We've gotten much better at the final step of this EV3, which is showing that a subset is indeed a subspace. Most of us have stopped trying to use single examples to prove something, and we are now looking at these sort of more general things. So in order for something to be a subspace, as we've said, it must have closure under vector addition and closure under scalar multiplication. Does not matter which you do first. So let's just do vector addition first. No need to label, but never a bad idea. So first things first, we need to start with two vectors that are in our space R already. We can define these vectors as x, y, z. That's in my space R. And let's also say A, B, C is in my space. All right, my potential subspace here. So if both of these are in that set that we're talking about R, then we get these things for true. So there we have this. If this is true, then we know. I'm going to rearrange this. 0 is equal to negative 5x minus 4y plus z. And 0 is equal to negative 5a minus 4b plus c, right? These, if they're in R, this must come with it for free. So our goal is to show that if I add these two vectors together using vector addition, that the result is also in R. It is important that I have all of these statements about things being in R. There's really no other way to write this. I had students sort of writing things like R equals and then some other thing like Z equals, but R is an entire set of like an infinite number of vectors. And so it's not the same thing as being like, hey, here's one particular vector from R. We can't add, like I don't even know what it would mean to add two sets. I think we'd be just looking at the same set because they are the same set. And then some students defined R as something. It was just, there was some mess here with that communication. All right, so if we want to show this, we now can do vector addition. We know this because we've defined vector addition is just adding the individual elements of the two vectors. In order for this to be within R, we need the following to be true. 0 is equal to negative 5 times that, the first element, minus 4 times our second element, and then plus our third element. And then we could do a little tiny bit of work here to say, okay, let's just rewrite this with all of the x, y, z pieces near each other, right? Let's utilize our like associative community properties. All of those second pieces together. We'll do our distribution. We know this is equal to 0. This is equal to 0. So this is true, right? We have proven that our sum of these two vectors under vector addition is still in our space. Beautiful, we got closure. So we okay, that's half of it. I have to show scalar multiplication. I also have to be general about this. I've already said that x, y, z is in R, so I'm just going to leave that there. I'm going to say let's choose some c in the real numbers. I don't love that they use R to define a vector space, but this is where we're at. We're going to use that double line R to say c is a real number. It's some random scalar, right? Some scalar we have not defined. Any scalar, really. And we want to say the goal here now is that c times our x, y, z is also in R. So we want to show that cx, cy, cz, that vector is in our R. And we know that's only true if it fits our beautiful rule. So 0 has to be equal to negative 5 cx, negative 4 cy, and cz all added together. We know that then we could factor out our c. Oh, and then we're back to the thing we said was equal to 0, and anything times 0 is 0. Boom. Done both pieces that we need to do. Last thing we need to do is write our conclusion. All right, since R is closed under vector addition and scalar multiplication, R is a subspace. Woohoo! Done. Conclusion written. I stated both things that I showed up above. I explained that this meant that R was a subspace.